One short question.
No, just one quick to go on that. Maybe at next year's Endeavor, we can have like a labeling party.
Yeah.
I mean, this is 800 people here speaking so many different languages, and we can get together and...
I'm so keen on a labeling party. I'm keen on just running this online. We'll have like because you ran an unconference, we'll run a labeling conference. And we all just get like, I wouldn't say we get drinks, but let's not label while drunk. It seems like a bad idea, or maybe it's better. Yeah, good idea.
Is Sebastian? I think a lot of you know.
Cool. I think, yeah. Can you all hear me from the back? Yeah.
Can you hear him?
Can you hear me?
I can force him to use the mic. Do you want me? Yes, they want me to force you to use the mic.
Okay, the second, okay.
Is it working?
Yeah, I can. Otherwise, I can also speak. Can you hear me if I speak like that? No. No. Okay. Fair enough. That was loud and clear. Thank you. Okay. All right. So in the spirit of this session, I'm gonna follow up a bit in the direction that Jade already started in how we can use machine learning and NLP methods, in particular for low-resource language. And the topic of this talk, or for kind of overall in the session, we asked the presenters to talk about and identify a big problem, in their opinion, that is faced by current methods in NLP. And I mainly want to talk about a particular dimension of one of the problems that we already identified in last year's session on NLP, which is mainly getting NLP methods to work on low-resource settings. And in particular here, given kind of our focus and our location, I particularly want to talk about how we can apply current NLP methods to all of the world's other languages, in particular many of the low-resource languages we have here in Africa. So that we can not only use our models just for English, but that they're able, that we can reap the benefits for the remaining speakers of the world. And in particular here, in a lot of research papers, when you read them, you kind of see the caveat that the model cannot be applied to another language because enough label data is only available for English. And kind of in classic NLP, really the main paradigm was generally that we would typically develop language-specific methods for NLP. So we would seek to develop a method that was particularly suited for English or for another language and just train that on data of that language. And if we wanted to have a method that worked for our particular language, we would have to go out there and actually label and annotate new data in our language to have a model that works for that language. And together with that comes a lot of language-specific pre-processing and just a lot of kind of modeling choices and choices in terms of data processing that are very language-specific and don't really generalize well to other languages. And now, lately, with the advent of deep learning and kind of neural vector representations of words and larger units of text like documents, we've recently seen in some of the early talks that we had in the previous session the success of methods that learn representations based on large amounts of text. And we can apply kind of a similar paradigm or similar methodology for cross-lingual NLP as well. So now, instead of trying to develop methods that have to rely on the labeled data in each of those languages, we can instead try to learn cross-lingual representations that are shared between different languages and on which we can then kind of only learn task-specific features for each task. So generally, the focus of this talk is essentially in terms of how we can learn these cross-lingual representations in practice and how we can scale these to settings where we might not have a lot of supervision to learn them in the first place. And in particular, I want to focus on 4 different aspects during this talk here. Firstly, the first 2 parts of the talk mainly focus on some of the work in learning these representations on the word level, which is where most of the work has been focusing on. The second part focuses on a bit more of a recent aspect in how we can learn these word level cross-lingual representations without any sort of supervision at all. And then secondly, I want to spend a bit more time focusing on a few more recent approaches which scale these cross-lingual representations to some of the deep pre-trained language models that we've seen recently, like Elmo and BERT. And finally, in the end, I'm going to just try to give some pointers and in particular references in terms of exciting open directions for research and hopefully give you some ideas for your own work in this direction. So starting with the first part of the talk here, so just to get us all on the same page here, cross-lingual word embeddings, or most current approaches for cross-lingual word embeddings, really start from the starting point that we have monolingual word embeddings that are trained separately on different languages. So in our case here, we would have used our method of choice for learning word embeddings like word2vec or gloth, and apply that to our unlabeled corpus in the languages we're dealing with. So we would learn a separate word embedding space for English here and another space for Swahili in this case. And now most currently successful methods for learning now cross-lingual word embeddings basically rely on learning a transformation function. So they rely on translating or of transforming one of these embedding spaces into the other one. And in practice, how that looks like is that you essentially try to learn simply a matrix that is usually called W here that allows you to transform. So you basically take the word embedding of one word in the other language and you essentially try to transform and rotate it in some way that it gets close to the corresponding translation of the word in the other language. And as you can see here, in order to be able to learn this transformation, you need some supervision in terms of knowing which words in the one language actually translations of the words in the other language. And in practice, the easiest approach then to learn this sort of transformation matrix is then simply to minimize the distance, so to bring the transformed embeddings of the source language closer, as close as possible to their counterparts in the other language with regard to some distance metric, like L2 distance here in this case. And in practice, what is really nice about this problem is that, so this was kind of the earliest approach that was proposed in 2013 and that Stefan in his talk earlier briefly pointed out. And what people have afterwards in the subsequent years found is that it's really useful for this W matrix to be orthogonal. Because that then, when you multiply one vector with an orthogonal matrix, basically retains all the relations between the words after the transformation. Yeah, so you still have kind of the similar, the words after they're transformed are still going to be in similar neighborhoods as in the original language embedding space, which is a useful property in this setting. And the nice thing then is if this matrix is constrained to be orthogonal, that you can analytically construct or calculate this transformation matrix simply by solving a singular value decomposition. So SVD here, which in practice can be done very fast just with an algorithmic solver. So in practice, it's very nice that a lot of these recent approaches are very easily applicable and very easily scalable and can actually be implemented in about 10 lines of code in practice. And there's lots of open source work in this direction, which I'm going to point to in the end as well. So just want to make sure, are we all, was this so far clear? Are we kind of on the same page in terms of how we can map one space to the other space? Cool. Okay, great. So now from here, I want to kind of segue to unsupervised approaches. And one thing that is useful to know is that many of the most recent approaches don't really start from an initial seed dictionary of these translation pairs, but then try to refine the seed dictionary over time. So how this essentially works is that you try to learn you start out with initial seed dictionary here. You learn this mapping in a first step by solving this SVD problem to get your transformation matrix. And then you apply that transformation to your source embedding space to translate your source words to the target words. You get, based on the nearest neighbors, kind of possible translation pairs. and you use these pairs now as a new seed dictionary, basically. And you could do that kind of repeatedly for a couple of iterations. And in practice, that particularly works well if you only start out with a small number of these translation pairs. So these approaches have been shown to be able to learn reasonable cross-lingual word representations if you start out with as little as 10 to 25 of these translations, just by the property of being able to refine kind of your dictionary that you use for supervision over time. And now, most recently, and the interesting aspect here is that this initial dictionary can either be given through initial supervision, but it can also be learned. And that is the main aspect where supervised methods differ from unsupervised methods. So the unsupervised methods are basically exactly the same as the supervised methods in this setting, with the main difference that instead of giving the model this set of translation pairs, you try to identify these translation pairs in an unsupervised way. And there's been quite a few different approaches that have been proposed for this kind of over the last 2 years. And I just want to mention one particularly influential one that actually Jade already hinted at in terms of the news approach by Facebook. Just to give you an idea, roughly some of the methods that have been used in this space. And this approach might also seem familiar to you if you come more from a computer vision background or if you've heard of generative adversarial networks in general. Because the main two components of this approach is essentially a generator and a discriminator. And what is interesting here is that they're used in a somewhat different way from your typical image generation task. So instead of now using some kind of noisy code that is fed into the generator to generate your target image, instead you feed into your generator your word embedding in your L1 in your source language. And now the generator tries to generate to again translate this word into an embedding in the target language. And in contrast, the discriminator's job now is to tell this transformed word from the source language apart from the true words that come from the distribution of the target language. And to basically make the decision whether this is actually a true word from the target language or just a generated or transformed word that comes from the actual source language here. And in practice, really, or generally with GANs, GANs are really powerful because we can try to learn a generator that tries to match the distribution of our target language or of our target data as well as possible, not just for individual target points, but kind of across the entire embedding space or across the entire distribution. And in our case, really the kind of the hypothesis or the motivation for why this setup should work in practice at all is that by the best way to translate or the best way to make the source space similar to the target space is by putting all of the source words close to their translations. And this really kind of, if you think of that, transforming that and finding an alignment that kind of makes the source space as similar to the target space, really kind of underlies the assumption that the source and the target language embedding space have very similar structures. So if we look again at kind of the initial example in terms of the supervised alignment here, where we, based on our translation pairs, we try to map the source embedding space close to the corresponding translations in the target language. Now, if we just go back to the setting, but actually remove the supervision, so we are just now given some words in the source language and some words in the target language, and now we have to find an alignment. You can basically conceive or imagine this process essentially of the model kind of iteratively trying to minimize some sort of distance measure between them, so of trying to rotate and align the embedding spaces in some way that over time essentially you have most of the points are going to be close to the other points in order to minimize the difference between distributions. And you hope then in the end that if you find kind of the best alignment there, then that then now in this alignment you would also get the translations to be close to each other. And now just to give you a brief example or brief illustration just from the conceptual level, how this actually looks in practice. It's actually fairly straightforward here. So now our generator is essentially not even a deep neural network, so it's just parameterized in terms of our transformation matrix W here. And our discriminator is just a neural network, basically, that tries to differentiate between, again, these transformed examples that were projected from the source embedding space X using our W matrix from the examples from the actual target embedding space Y. And in practice, then, we have, as in the typical GAN setup, essentially two losses that are kind of competing with each other. So the discriminator essentially tries to minimize this term here, where we basically try to minimize or maximize the probability of being able to assign the correct label. So where a 1 is here kind of the correct label that is fake. Yeah? So we want to be able to say that the transformed examples are fake. And that the examples from the actual target distribution are true examples. And in the generator's case, we essentially try to do the opposite. So we want to maximize the probability of fooling the discriminator in assigning the wrong label in each case. And this can then basically be optimized as usual with standard stochastic gradient descent by iteratively, one after the other, updating both the discriminator and the generator. And as is typical with GANs, there's a couple of tricks in terms of like hyperparameters and different settings that that are required to get that to work. So for those, I recommend you to look at the original paper. And now so much about kind of the additional kind of the technical details of this work. And now I just want to briefly highlight some of the results here. And what I think has particularly struck many people and what a lot of people found surprising is that initial results, when a lot of these unsupervised approaches basically came out, they really claimed that this unsupervised approach was really competitive with many approaches that rely on supervision as well, which is quite counterintuitive that you can, in a completely unsupervised way, but just getting this alignment from your data, you can be as good as if you were given these translation pairs in the first place. And this in addition, it's an interesting question to ask because in practice, online through different sources like Wiktionary and other publicly available dictionaries, there's actually supervision data to train good supervised approaches. So it's really a question if these unsupervised approaches are actually useful in practice and achieve performance given that supervision is easily and readily available. And in that context, we've conducted some recent studies on particularly looking at one task that is known as bilingual lexicon induction, where you essentially have a Go dictionary of translations and you use your cross-lingual embeddings to find the corresponding translation as the nearest neighbor of that corresponding source embedding. And that's kind of a common task that is used for evaluating these cross-lingual word embeddings. And we've looked in particular at kind of different language pairs. So this is like always from English to different other language, comparing this unsupervised method that I've just talked about to kind of a comparable supervised approach. And what we've seen here is that these unsupervised approaches actually fail in the most challenging settings. So in settings where the source and the target language are quite different from another. So here, this would be English to Estonian, English to Finnish, or English to Greek. Whereas English to Spanish would be, in comparison, two more similar languages. And the main reason for why this failure happens is essentially based on the assumption that I mentioned before, in terms of assuming that in order to produce this unsupervised alignment, we require our embedding spaces in the different languages to be as similar as possible. And we've looked a bit at how you can actually characterize the similarity between different embedding spaces by looking at the nearest neighbor graphs of these words. And in particular, a lot of these approaches relied kind of on the assumption that these embedding spaces are approximately isomorphic, so that the nearest neighbor structures, or kind of that the neighborhoods in which the words are ranged in each of the embedding spaces have the same structure, and that each of the words are connected to basically a similar number of words in the neighborhoods. However, in looking at that and actually looking at a metric and inspecting the nearest neighbor spaces, we found that this does not actually hold in practice very much, and even just looking at, and is only limited even for related languages. And in particular, we've proposed a metric to characterize this distance that looks at some initial characteristics and properties of these nearest neighbor graphs as characterized by, here in this case, their eigenvalues, which kind of describe in a very concise way some of the structure of those embeddings. And exactly relying on kind of the ratio of the eigenvalues here. And in particular, we can look at, if we look at the performance and correlate that with this sort of similarity or dissimilarity measure, we can actually see that for very related language, we get a corresponding low dissimilarity value, whereas, which means that those embedding spaces are very similar in terms of their nearest neighbor structure, whereas for the more distant languages, we get a very high dissimilarity value. So the performance of these unsupervised methods actually very dependent on how similar the structures are of these different embedding spaces. And now I just want to just briefly mention going from these word level representations to some more deeper representations. And in particular, you've already heard before from some of these deep pre-trained language models that train models typically based on transformers on large amounts of text, and whose representations are quite useful for a lot of different downstream tasks. And here also we've seen quite recently, as you can see from the references here, this idea has been extended to also learning cross-lingual representations. And one kind of key interesting point here is that all of these approaches essentially share the vocabulary across the different languages. So they use the same byte pair vocabulary across different languages, but don't rely on any other form of supervision. So they just train a model like BERT on to concatenated corpora from different languages. And just by doing that, you can actually, which is very easy to implement, just using your monolingual models, you can actually learn fairly reasonable and surprisingly effective cross-lingual representations. And with an optional trick in the beginning, particularly for more distant language pairs, in using some of these cross-lingual word embeddings to initially bias your model towards a more cross-lingual embedding space, essentially. And as we've seen in some recent studies at ACL and other conferences, these representations perform surprisingly well on many downstream tasks. However, again, with these very deep models, they are very expensive to train and are quite large as well to run at inference time. And another kind of failure case of these models is that given some of these methods are trained on very large, on a large number of languages, and given that the entire vocabulary is shared across many languages, it's often that low resource languages for which not a lot of data is available to learn that vocabulary in the first place will be underrepresented and over-segmented based on the vocabulary. So we've seen in some recent work actually that because in a lot of settings in downstream tasks that you care about, you often have like a limited number of samples available, or it might be possible to annotate a few hundred samples. And we've actually seen recent work that in many of these cases, actually smaller, comparatively smaller and more efficient monolingual models are competitive with some of these more huge, bigger pre-trained models that require large amounts of compute and large amounts of pre-trained data. And I'll mention some resources on that in a second. And now finally, I'm just gonna briefly, I think I have most of the directions here on one slide anyway. I just want to highlight and give a few pointers in terms of interesting kind of future research here. In particular, kind of recently, as I mentioned, this task of bilingual lexicon induction is something that is typically used for evaluating these sorts of representations. However, people have identified already different problems with that task. So looking at different alternatives in terms of other tasks you can evaluate your models on, or proposing different means of improving that task that maybe are particularly suited for your language of interest is a really is an important research direction. Secondly, and I think probably the most important one of these, really, as I kind of illustrated before, the main and I think the biggest problem really is to get these kinds of methods to generalize to low resource and distant language pairs that are very distant from English. So I think overall, and in particular, coming up with approaches that deal with the characteristics of your particular language, whether they are agglutinative, have a very rich morphology, have very different cases, or just very different structures in the embedding spaces. Finally, I think as well, these types of multilingual representations that I mentioned before are very, very recent. So we only have a very limited understanding so far of what they're actually capable of and what their failure cases are. So really kind of analyzing them, training them for your own language, looking at the results, looking at the representations and the embedding spaces that are learned, and trying to kind of see on which tasks or which examples these fail, I think is a very, very important research direction. And finally, I basically mentioned kind of the most prominent current approach, which is based on learning this mapping between source and target languages. But in practice and kind of in the history, other types of methods that rely on other kind of sorts of alignment between the data, like parallel corpora or even pivoting through images, have been proposed. And these can maybe remedy some of these problems in terms of generalizing or bridging this similarity gap between different languages. And finally, I think a really important and really interesting direction is also, as I kind of mentioned here, these particularly distant languages have very different embedding structures. So maybe looking at these embedding spaces and seeing whether we can gain some understanding and use that to gain more knowledge about how different languages interact with each other, what their similarities are, or how, in what cases they can translate or not translate to each other, I think are really, really valuable. And finally, I just want to stress again, I think particularly this setting in looking kind of at the hardest setting of getting them to work for your for your own low resource language, I think, and not in terms of just what most people have done so far, just looking at European languages, but actually focusing on these hardest languages, I think is kind of the most important thing you can spend your time on, basically. And with that, here's just a number of references in terms of papers, kind of some useful starting points. Both a recent survey that I've co-written, which essentially summarizes most of the history that precedes what I talked about now, as well as a recent tutorial that I gave that gives you a bit more context on these unsupervised representations, as well as a collection of recent papers that basically kind of points out and expands on some of the issues I mentioned. And again, the nice thing about these types of approaches is that most of them are actually open source available. So there's lots of approaches like the VecMap and Muse method that you can just download yourself and apply to your own data, as well as these recent bird type models are also available online. And on the last link, we soon have some more monolingual language models released as part of the Faster AI framework. So if that's something that you're interested in terms of training a monolingual language model in your own language, then talk to me later as well. Yeah, cool. And just as a final disclaimer, if you're interested generally in doing like an internship or working in research on NLP, we're also hiring at DeepMind. Thanks.